Okay, welcome everybody to the INQA seminar for today, the 19th of November. My great pleasure to introduce today's speaker, who is Stéphane Louise. Stéphane is from CEA. We'll be talking to us today about using maximum cardinality matching GN series as a benchmark for quantum computers. Over to you, Stéphane.
Yes, thank you for the introduction. So I am Stéphane Louise, as was introduced, and I will present here mostly the research work of my former PhD student, Daniel Ver, but with extensions from our collaborative work with the ULIC Center for Supercomputation. So in this, first I will introduce what are the D-Waves quantum computers for those who are not familiar with this. So D-Wave is a Canadian enterprise already quite old in the field, and it is a commercial provider of quantum solutions since 2009, with several generations of QPUs from 100 or so qubits to the current one with over 5,000 qubits. The next generation was planned for this year's, I guess maybe next year's. I had some rumors about D-Wave. Nonetheless, they are still seems to be okay. And there's already really quantum leaps in the quality of the qubits and the connectivity of these different QPUs over the generations we had. These are superconducting qubits, Novium loops, and the principle is quantum annealing. So it's kind of analog quantum computing, which is not it's very separate from gate-based quantum computing. So the different generations of QPUs consist of the oldest one, which is not now retired, with the Chimera architecture, which had 6 connections per qubit. The Pegasus, which is the current one on the Advantage machine, has 15 connections per qubit, and the Zephyr, which already is in preview on the prototype, has 20 connections per qubit. We will see that even though we had a very nice progression in the number of connections per qubit, is still very sparse at the level of what we want to do with usual optimization problems. The basic problem that can solve the D-Wave machine is the Ising Hamiltonian. So it's this form with, I hope you can see my pointer, not sure anyway, which is a biased spin, which is spins in a biased magnetic field, and coupling between spins. Usually in the z-axis. We will see that is equivalent of to an optimization problem, which is called QUBO for quadratic and constrained binary optimization. So any QUBO problems can be expressed as a binary vector X, and with this kind of matrix, which provide a quadratic expression of the of the cost function. This is trivially equivalent to the Ising Hamiltonian that we see above by simple variable substitution. And what is relevant for using the D-Wave QPU as computers, something to solve a problem, is the adiabatic theorem of quantum mechanics. Therefore, if we have a Hamiltonian that evolves through the time, if the evolution of this Hamiltonian is slow enough between a base Hamiltonian, which is called the driver in general, and the target Hamiltonian, which represents your problem, we will stay on the fundamental state of the time-dependent Hamiltonian for the time. That means that if you have annealing schedule F this way, at the end of the annealing time, you will have, if you start with the basic state of the driver Hamiltonian, which is usually easy to solve and to configure, you will have at the end of the annealing process the ground state of the target Hamiltonian, which is what you want to solve in general. So the adiabatic theorem is quite complicated. It depends on the spectral gap, what is called the spectral gap of the Hamiltonian, which is a parameter you don't have access to. That is why instead of using directly the adiabatic theorem, the D-wave machine use a heuristic that try to approximate the adiabatic theorem. So it's a heuristic called usually called sorry the quantum annealing, or also the adiabatic processes, which is an approximation of the adiabatic theorem. So one of the important limitations, as I said before, of the D-wave QPR architecture is the number of couplers per qubit. That means that we have a sparsity of the adjacency matrix in the in the graph. You can map your problem with which we can map your problem. So if you have a problem with a general QUBO problem or a general Ising problem, you must fit with the architecture of the D-wave machine to try and map your problem on the machine. As the connectivity is very sparse, it incites the use of kind of logical qubits or something like that. That means utilizing more than one physical qubit to map one logical variable. And therefore appears the problem of minor embedding. We will discuss that more thoroughly thereafter. Generally speaking, the Ising problem or the QUBO problem is a NP-hard problem. And as there is an equivalency path from one NP-hard problem to another, if the D-wave machines would have been working very fine, would be perfect, then the D-wave machine could solve any NP-hard problem. So, of course, one of the obvious target of D-wave QPUs is to be good at optimization problems. Nonetheless, we must be very careful of the fact that we need to build logical qubits because of the minor embedding problem. And the minor embedding problem itself is a NP-hard problem. Of course, you don't want to solve an NP-hard problem to solve another NP-hard problem, especially since the minor embedding is most of the time harder than the initial problem you want to solve. Therefore, we use heuristic to make minor embedding, which we hope to be good enough. Then there is other parameters like the coupling strength within a logical qubit. We will talk about that later. And in general, the complexity, because of the minor embedding, is much higher than the complexity of the initial problem. So what is minor embedding? The principle, mostly speaking, is let's say you have a QPU with 4 coupling per qubit and a problem with 5 coupling. You have 5 qubits here, 6 qubits, and you want to have a non-trivial coupling within each of these 5 external qubits with the internal qubit here. Of course, if you have only 4 qubits coupling per qubit, you cannot do that directly. The obvious answer is not difficult in that case, is to use 2 physical qubits to map the inner qubits here. This way, you can connect all the 5 qubits. You can, in theory, also map 6 qubit here with a kind of logical qubit which is shared on two physical qubits. So one parameter that is important is how you decide to split these logical qubits into physical qubits, which is, as already said, NP-hard problem in the general case, even if here it's quite easy. And the other one is the chain strength. That is to say, the coupling you impose between the physical qubits in the inner logical qubit. And this is usually expressed as a ratio called a relative chain strength, because you utilize the coupling already appearing in the graph to impose a ratio, corresponding ratio between your physical the chain of your logical qubit and the problem you have. So then, as the base is set now, we want to find a problem to solve with our QPUs that would characterize well the capabilities of our QPUs, and can also show how it will improve in the future. So one way to do that is to find a combinatorial problem, which quite simple to evaluate optimum values. For example, that is what is done by Atos with the Q-score. And the Q-score is based on the max cut problem, which is an NP-hard problem, but unconstrained. That is one way to do it. In this case, the optimum is evaluated on the statistical basis on its depending on its cost. But in our case, we utilize the polynomially hard problem, only polynomially hard, which is the Maximum Cardinality Matching, or MCM for short, and especially the GN series, that was defined by Sasaki and Hajek in 1988. So matching is basically speaking, is a matching between two single element of a population. So it's a constraint problem. You only have one bound between two elements of your population. And a maximum matching is a configuration of matchings that maximize the number of matching. But the GN series is a special instance of the MCM, which is easy to solve by construction. And it demonstrated, the Hajek and Sasaki and Hajek demonstrated with this series that the simulated annealing can be a slow convergence in some cases. Why? Because there are n plus 1 at the power of 3 possible matchings in the graph, but only 1 plus 1 at the power of 2 in the optimal solution. So selecting randomly a given matching is increasingly counterproductive as n grows. So this is a good candidate to complement the Q-score on optimization problem, because on the one hand you have NP-hard problem but unconstrained, and on the other hand you have a polynomial problem but constrained. What what is the design of the G series? So this is an example of the G3 instance of the series. And you have a population of A nodes and B nodes that are that can link this way. So you have in the case of G3 4 lines and 3 densely bonded bipartite graph, sub-bipartite graph, and 4 simply connected graph between A and B. And the optimum solution by construction is very easy to find, because it's the simply connected couples A and B in this case. So it's a trap for simulated annealing because of the probability it has to select a bad bond between A and B. So there is a high chance to select one bond, one link in the bipartite portion of the graph, and therefore it's a good trap. And we will see what can be done with quantum annealing on this kind of graphs, series of graphs. Nonetheless, as this is a constraint problem, we have to map it, to convert it to a kind of soft constraint problem by changing the economic function of the and taking the constraint into account. This can be done. I will not be very go deep with that, by using a constraint that the cost of using more than one link in the graph will raise the cost by the number of constant that is proportional to the number of edges in the graph. In the case of G1, you can see that G1 is very simple graph. This gives this kind of cubo matrix for the formulation of the cost function, which is quite easy. It is worth noting that in the future we will simplify the cubo formulation of this graph, because it's very easy to find out that mostly the diagonal will tend to -1 if you normalize the problem, and the non-zero coupling will tend to 1. One point to note is that when n grows, the number of edges per vertex grows linearly with that, and therefore we will have rapidly an issue for embedding. The G1 instance can be mapped without a minor embedding. Already with G2, we have to do some minor embedding because of the number of coupling we have in the graph. So if we compare the outcome on the older architecture, which was Chimera architecture, we at the time of the PhD work of Daniel Ver, we worked with the D-Wave 2X machine. And we only had the opportunity to work up to the G4 instance, G1 to G4. And this is the same with the D-Wave 2000Q machine, which was also limited to G4 because of the embedding problem. So with 2000 qubit, you only can map something with about 125 variables. It is worth noting that at the time there was little influence of any parameter on the outcome of the machine. On the newest machine, we've done a work with the Jülich Center for Supercomputing on the Pegasus and Zephyr machines, which have a much higher number of couplings per qubit. And therefore, we studied the influence of the annealing time to the number, the influence of the minor embedding through the number of qubits within a minor embedding, and the value of the relative chain strength. For the first parameter, it was we made a simulation of the Schrödinger equation, and we compared it to the result of quantum annealing on D-Wave. You can see that on simulating the Schrödinger equation will lead to a good result for within 10 nanoseconds. On the real hardware, nonetheless, this is not a real process of adiabatic annealing. The problem will need a bit more time, but if you compare to 20 microseconds, which is the annealing time by default of the D-Wave machine, you already have 100% of good result on the Zephyr machine with the G2 problem. Okay, for the relative chain strength problem, you have to tweak the parameter to optimize the outcome. You can see that with a relative chain strength that is too low, you will have not have the correct result at all. If you put the relative chain strength too high, also you will have a low probability of finding the result of your problem, because the Hamiltonian you want to solve will be mostly dominated by the chain strength. So you have an optimal value, which is around 0.5 in this case. It depends on the problem, really. And the impact of the minor embedding is also quite relevant. So we spent some time to find somewhat good embeddings for the problems because we saw that it has a really high impact. So in purple here, you can see the number of variables in the G series up to G7. And for the oldest generation, you can see that you need around 1,000 qubits to map a G4 problem. The advantage machine has up to 500 qubits, so you can map up to G7. And the Zephyr prototype, which at the time had only 500 qubits, now it's a bit more, could map up to the G4 series. And you can see that there is a very significant impact of the number of bounds in the architecture, as you could easily imagine. But it's also translated in the quality of the result. If you pass some time to find some better embedding, especially with the advantage machine, you will see much better results than with not optimal, not far from optimal embedding. So with good embedding, what we can see is that the old generation of machine can barely find a solution for G3. For the advantage machine, which is a current commercial machine, you can quite easily find the solution for G3. But the prototype is quite impressive because it has a really good probability of finding the solution for G3 and even has a non-zero probability of finding the solution for G4. Beyond G4, it's not worthy of finding. It's not good enough to find a solution. So, as a conclusion and some comments on the result, the GN series is a really good benchmark for quantum computers. It characterizes the progress of QPU machine architectures, and it also shows the dependency of the outcome of the QPU on the several parameters you can have as the inputs. There are also other papers that use this problem to find to try and find the solutions of the G4 and try to probe the capabilities of this machine. For the comparing the QPUs with the standard, the classical computers, we have shown that when compared to simulated annealing, simulated annealing is better than quantum annealing on the initial problems. But when we take into account the fact that we have to embed our problem because of the sparsity of the architecture, then in this case, quantum annealing is much better than simulated annealing. And in any case, it has the advantage in most of the case that it gives a good enough solution in a really short time. Typically, in less than a few milliseconds, you have a good number of samples, typically 1,000 of samples for your possible solution of problem. And within that, usually the best solution is not so bad. And on the future, it is worth noting that we will use that as part of the French applicative benchmarking for QPUs in the BACQ initiative that will be also proposed as a basic for Senelec and maybe ISO goals of providing metrologics on QPU performance. So thank This is the references. And thank you for your attention. If you have some question, I will be happy to answer.
Good. Thank you very much, Stéphane. Very interesting. Thank you. And as Stéphane says, this is now open for questions. If you have a question, just speak up or raise your digital hand if you wish.
Yeah, I have one question.
Go ahead.
Yes.
Well, thank you. Very nice talk. I have a question about these are polynomial time problems, right? These are not NP-hard problems, right? If I
No,
understand.
not at all. That is, this is one issue if you want to gauge the capability of quantum computers on optimization problem. Either you have NP-hard problem, then you don't know the solution, or you have polynomial problems that can be still combinatorial problems like GN series, but easy to solve, and you have the optimal solution.
But the optimal, so the polynomial algorithm for which you get the optimal solution runs much faster than either simulated annealing or quantum annealing. Is that correct?
Indeed. Yes, indeed. On this kind of yes, this is the kind of problem that is only relevant for benchmarking, not for any kind of purposes outside of finding how good the quantum computers or the your optimization heuristics are.
I see. So if you say the problem with using NP-hard problems is that you don't know the
Yes.
optimal solution, but you could
Yes.
compare the simulated annealing with the quantum annealing solution, right? So
Yes.
you get a time and you get a quality, and you can make a
Yes.
scatter plot
Yeah.
of time
That's
quality, and you get.
yes. That is basically what we've done in the PhD thesis of Daniel Ver, and what we observed, as I mentioned in the conclusion, but is that simulated annealing, then most of the time it is also true for other kind of annealing solution on classical computers like vector annealing or digital annealers. You have a time to solution on the initial problems that is good and sometimes better than the quantum annealers. But once you take into account the embedding, it's generally worse. And even for G7, what we have seen, even in the initial problems without embedding, most of the
Sorry,
time
but the G7 is a
it
but
is quite
G7
large.
is
Is
a polynomial problem.
already several thousand of variables. Yes, indeed.
But I
And
thought you were talking about tractable problems. So I thought you were saying something about my question that I say, what is the comparison in terms of
yes,
time
if
quality
you
for
compare the on G7, if you use a simulated annealing, which is a sequential algorithm, you will take days typically for G7. On vector annealing, which is a solution by NEC in Japan, you have a solution that can be brought in a matter of minutes. On other digital annealers, you have on the initial problem. Sorry. And on the Fujitsu digital annealers, I don't know because I didn't test it, but I guess it's the same order of magnitude, several minutes to have the solution. But on the initial problem, you will have the exact solution up to G7, I guess. After G8, it's very difficult. And once you take into account the fact that you have an embedded problem, you see that quantum annealers are really good to find something, even though the problem you have initially is very is obfuscated by the embedding.
Okay. Thank you.
I see that Haida Salman has his hand up patiently.
Thank you. Yeah, thanks for the talk. My question actually is just related to the capabilities of current hardware. I mean, I'm just trying to get a sense of what is possible. And you talked about the limited connectivity.
Yes.
But I'm also wondering, I mean, how much flexibility is there in changing the strength of the coupling? Because this of the general problems one wants to deal with, you can have, apart from just ferromagnetic, antiferromagnetic interactions, there can be difference of strengths across the graph.
Yes.
So I'm just wondering how much flexibility and whether one can deal with this kind of situation with some form of embedding, or whether there is a bottleneck somewhere.
So the limitation of the current of the D-Wave hardware is that you have to normalize your problem. So you're in the diagonal is the current QPU. You can have the diagonal between -4 and +4, and between -1 and +1 for the GIG. The GIJ coupling, the interspin coupling. Within this, so you have to normalize your coupling, of course, to match this spectrum of capabilities, and then within these bounds, the actual resolution, taking into account several limitations in crosstalks, in the precision of digital to analog converters and so on, is usually between 1/1000th and 1%, mostly speaking. So if you have a precision that is required below 1000, I guess it will not be seen accurately by the hardware.
I see. Okay. Thank you.
Just to follow on briefly the line of reasoning from Bert. I guess I also have concerns about benchmarking with easy problems.
Yes.
And I guess the thing that I would like to see, if I accept that premise,
yes,
would be a plot of something like time to solution versus number of qubits on a log-log plot, and then you see the slope of the which reveals the exponent of your polynomial scaling. Do you have that data?
With D-Wave QPUs, it's quite easy because you have a batch of 2000 samples within 1 millisecond. So each time you send a problem to a D-Wave QPU, you will be feedback with typically 2000 samples that would have taken about 1 millisecond of computing time in the QPU. Of course, there are lots of caveats within this 1 millisecond, because you have to configure the hardware, normalize the problem, and so on, make the embedding, and so on and so on.
Have you looked at the scaling of this and compared it with the scaling of simulated annealing?
Yes, mostly speaking, the time to solution, if you accept that you only have 2000 samples, is constant, mostly constant. So for the D-Wave QPUs, that will not be the same for maybe Pascal Pascal QPU that are also analog computers, quantum computers, but for D-wave computers, it's mostly constant.
Okay. Understood.
Mostly. It's the difference in time is not really irrelevant.
Okay.
Nonetheless, the probability of getting a solution, if you want an exact solution, will give you the time to solution in some way.
Okay, are there any further questions for Stéphane? If not, let's thank Stéphane again. Very nice presentation. Thank you.
Thank you for the opportunity.
We'll conclude there, other than to say that next week's presentation is to be given by Zhenya Mozganov. I look forward to seeing many people at Zhenya's presentation next week. Thank you, everyone. Bye-bye.
Thank you. Bye.